Hello everybody, welcome back to the Gaussian maths video. In this video I'm going to be starting an algebraic number theory series. Now, I would add these to my original number theory playlist, but if I go on to like the prime number theorem and some other analytic methods and so forth in number theory, then the order will get all messed up and I'd rather not have it like that. So I'm just going to make a whole new series for the algebraic methods and then put any analytic methods in number theory in the analytic number theory section. And so the first video about algebraic number theory is going to be the Gaussian integers. And the motivation for this whole video is going to be, how can we prove the following? And I found this pretty remarkable when I first saw it, theorem. So the theorem is, given a prime p, p can be expressed as a sum of two squares if and only if it's congruent to 1 mod 4, where a and b are integers. Now, if you think about it for long enough, this implication, so a prime being expressible as a sum of two squares, implying that p is congruent to 1 mod 4 is instantly obvious, because all primes are either congruent to 1 or 0 mod 4. So this right here is obvious. However, what's pretty incredible and much less obvious is that p, a prime being congruent to 1 mod 4, implies a sum of two squares. And that's what we're going to prove at the end of this video. And to do this, we're going to look at the Gaussian integers. So what are they? The Gaussian integers are just the set of all a plus bi. Now, if a and b were real, then we'd just be describing the complex plane, but they're not. They are integers. And there's actually a lattice in the complex plane. Now, we need to prove one important fact about these, and then we're just going to go straight in and prove this theorem right here. And the fact that we need about these is the following. So we need them to be a factorial ring, but we know that showing that they're a Euclidean ring is enough. So the Gaussian integers is a Euclidean ring. Is an ER. Hence an factorial ring. Alright, so let's just do the proof. So the proof is actually very neat. So we're going to show, we will show it's a Euclidean ring with respect to the function n, so it's the n standing for norm, which takes in a Gaussian integer and it outputs a natural number or 0. So it outputs a natural number or 0, and what it does is it sends alpha to its magnitude squared. Right, so this is what it does. And now, what we want to show by the definition of a Euclidean ring is that given Gaussian integers alpha and beta, such that beta is not equal to 0, there exist gamma and rho such that alpha equals beta times gamma plus rho. Now, there's a clever way to rewrite this problem whereby we can use the fact that the Gaussian integers are a lattice to prove the overall theorem. And the way to rewrite it is, I'm going to write it in red because it's important. So we divide both sides by beta, so alpha over beta, and then we're going to subtract gamma, so minus gamma, is equal to rho over beta. And then we're going to take magnitudes on both sides. And then look, oh sorry, I forgot to add the condition that by the definition of a Euclidean domain, you have to have this condition. Sorry, I forgot to add that part of the condition. And so therefore, since the magnitude of rho squared is less than the magnitude of beta squared, this right here, this magnitude right here, is going to be strictly less than 1. And so, what's left to show is that there exists a gamma such that alpha over beta minus gamma, the magnitude of it, is less than 1. So this is what's left to show. Now, how do we do this? Well, the Gaussian integers are a lattice in the complex plane. So there are integer coordinates with basis 1 and I, the complex unit. So they're a lattice, and so therefore any, let's say for example alpha and beta, any complex number is in a mesh of the lattice at least 1/2 square root of 2 away from a Gaussian integer. And why is this? Because this pretty much seals the proof, but why is this? Well, if you take a look at the complex plane, and we have a Gaussian integer here, then the next one here, in fact, let me draw this much, much bigger. So if we have a Gaussian integer here, and then the next one is here, where this distance is 1, and then the next one up will be this distance here, 1, and then the distance between these two Gaussian integers is going to be square root of 2, right, by Pythagoras, then the furthest away a complex number can be from any one of these is right in the middle here. And that distance right there is going to be 1/2 square root of 2. So that distance right there, that's the maximum distance a complex number can be away from a, not a lattice, a Gaussian integer. So that's why. So therefore, the completion of the proof is that the magnitude of alpha over beta minus gamma is less than or equal to 1/2 square root of 2, which is less than 1. And that completes the proof, as I've shown right here, which is what we need to prove. So now, we showed that the Gaussian integers are a Euclidean ring, therefore they're a factorial ring. Now, we can prove the original statement. And it's actually a neat application of Wilson's theorem. So, proof of original statement, which I believe is known as Fermat's theorem. Statement. Although I'm not sure if that's what it's known as. But I wouldn't be surprised, because he was, a great number theorist. Anyway. So, what we're going to show is that, if P is congruent to 1 mod 4 is a prime in the integers, then it's not a prime element in the Gaussian integers, basically. So now we're going to assume for a second that this is true, and then we'll come back round to proving it later. So, alright, so this is what, okay, so assume it's true. If true, P could be written as alpha times beta, where alpha and beta are non-units in the Gaussian integers. And so P squared is equal to the norm of alpha times the norm of beta, because the norm is multiplicative, and of course the norm of P is going to be the magnitude of P squared, which is obviously just going to be P squared because P is a real number. Alright, and therefore P is equal to the norm of alpha is equal to A squared plus B squared. Alright, so if this is true, then yeah, it does hold. It does hold. Where alpha equals A plus BI. So yeah, so if it is true, then it holds. But we have to show that it is true. So, alright, so how should we do this? So, we must now prove the original statement in this proof. In the proof. And to do this, note that there is a solution to x squared is congruent to negative 1 mod p, where again p is equal to 4n plus 1, right here. Now, what is the solution to this? Well, x equals 2n factorial. Why? Well, by Wilson's theorem, which I won't prove here, but you can look it up if you want the proof, or you can try and prove it yourself. So what Wilson's theorem says is negative 1, sorry, it's just negative 1. Negative 1 is congruent to p minus 1 factorial mod p. And this holds for all primes p. So, now, we're going to use this. So this is equal to 1 up until 2n times p minus 1, times p minus 1 up until p minus 2n. And this is because of this original fact here, which is that this implies that p equals 4n plus 1. Alright? So here we're going to have this up until 2n, and then times 2n, this is going to be 2n plus 1, and so on and so forth up until p minus 1, which is 4n actually. It's 4n. Now, note that because of this, so because p equals 4n plus 1, alright, we will have that 4n is congruent to negative 1 mod p. 4n minus 1 is congruent to minus 2 mod p, and so on up until 2n is congruent to Sorry, what's it congruent to? Mod P. It's congruent to minus 2n plus 1 mod P. I believe. Oh, sorry, 2n. What we want is that 2n we'll have 2n plus 1 is congruent to 2n mod P. Like this. And so now we have that P minus 1 factorial is congruent to now here we're going to have 2n factorial and then times, so we're going to have 2n factorial right here, and then this is going to be, so P minus 1, that's going to be minus 1, and then we're going to have minus 2 times sorry, it should be minus here, times minus 3 times minus 4 and so forth. So we're going to have negative 1 to the 2n times 2n factorial, and then this is equal to 2n factorial squared mod P is congruent to, so I'll just insert a negative 1 there quickly. Anyway, since it does admit a solution, we have it that P divides x squared plus 1, which equals x plus I times x minus I. But now, because the Gaussian integers are a factorial ring, for P to be prime element it must divide one of these. But since x over P plus or minus I over P are not Gaussian integers, P is not a prime element. Of the Gaussian integers. And that actually completes the proof. So that's very neat. So we used the Wilson's theorem to prove this statement, which proves the original theorem, which is that all primes which are congruent to 1 mod 4, so if they're of the form for n plus 1, can be written as a sum of two squares. So, for example, yeah, we have 5 equals 4 plus 1, 25 equals, sorry, 25 is not prime. Trying to think of examples now. Oh, 9 is equal, that's a square. God, I can't think of any primes congruent to 11, no, 13 for example, yeah, 13 is equal to 9 plus 4, 37 is equal to 36 plus 1, and so on and so on. Anyway, yeah, I hope you enjoyed that video, and yeah, I'll see you in the next one. I'm gonna probably be continuing homotopical algebra tomorrow, because I have holiday. I can actually upload videos, I'm hoping daily, if not once every other day. This holiday, where I'll be doing homotopical algebra and algebraic number theory mostly, I think. But yeah, whatever I do next time, I'll see you then. Goodbye.